In 2001, the AP Physics C Mechanics 3rd FRQ had us consider a vertical pole with a horizontal rod connecting two masses and a string wrapped around the vertical pole connected to a pulley and then to a block of 4M. And then they release the block of 4M, and as it accelerates downward linearly, the rod here, the vertical pole, is torqued and the whole upper system begins to angularly accelerate. And they start by asking in part A, what's the rotational inertia of this system? Well, in the instructions they say the vertical pole and that horizontal rod are ideal and they have negligible rotational inertia. So we're just looking at these two big discrete blocks of mass here, separate from the axis of rotation, which is along this region here by a distance L. So instead of trying to integrate through a continuous mass, I'm going to consider just a discrete sum. So I've got one mass, a distance L from the axis of rotation, and another mass, a distance L from the axis of rotation. So it's just 2ml squared. Then they ask us to consider what acceleration the block of 4m experiences as it moves downward. So this is a Newton's second law of motion problem where we've got both the 4m mass linearly accelerating because of those two forces. I know that the tension force pointing up is less in magnitude than the weight force pointing down because the net force points downward. So with this I'm going to apply Newton's second law of motion. I'm going to keep track of the amount of mass I have that's accelerating because of those two forces. The College Board is purposefully hoping that we'll put an M here and lose track of the fact that it's worth 4 M's. It's just how they roll. So I'm going to lead with my larger vector, keeping everything as a vector sum. And then I'm going to choose a coordinate system that shows the downward direction to be the positive direction. And so I'll have this is a positive in direction, magnitude is 4mg, tension force is negative in direction, upward, its magnitude is the tension here. And this equation has two unknowns, the acceleration and the tension. So I need a second equation to solve for the acceleration. So what I'm going to do is focus on what's happening right here with the string torquing that vertical pole. Now I'm going to rotate this pole and draw a diagram that looks more like this. So here's the radius r, there's the axis, and then by a rotation of 90 degrees, I can look at sort of the inside of that pole, and here's the string coming off like this. And this is the tension force here pulling the string to the right. So I'm going to sum up those torques, set them equal to I alpha. I want to choose a coordinate system that's consistent with positive angular acceleration. So I see the system's going to rotate with into the page, and so that'll be my positive direction. And now I'm going to sum up this just single torque there. So it's the torque from the tension, and then specifically that's a positive torque, and its lever arm is little r, and the force torquing is the tension. And I'm going to write this as an instructional tool, sine 90, because of the angle between the lever arm and the force is 90 degrees. That's just 1. And then the rotational inertia I found earlier to be 2ml squared. And then alpha, I'm going to translate everything into these linear variables. So I'm going to use that the tangential acceleration is r alpha. And so I can write alpha as a over r. Clean this up a little bit here. So I'm going to write this one as, it's two equations and two unknowns. So I've got this, And I want to take this r and multiply it on both sides and make this one an r squared. So my goal is to solve for the accelerations. I'm going to try to eliminate tension. So it seems like my preference is going to be to do this, right? A 4mg minus 4ma, and set it equal to the tension, and then take this tension equation and substitute it into here. R squared I'm going to distribute. Divide out all of the m's and group together the a's. And then before I divide, I'm going to factor out a 2. And now I'll divide and come up with my final answer. This is not a common form for acceleration I'm used to, so I'm going to do a quick unit check. And the units of acceleration, let's see, I've got in the numerator here, I've got a meter per second squared with the g, and then that is a meter squared. And then down below, it's meter squared and meter squared. So these will cancel, and I've got a meter per second squared for my units. So as long as the units work out, I feel confident that I've done the right work here. I'm not guaranteed, but it's nice to check to make sure the units work out. Part C is asking, what happens when this 4m block falls downward a distance d? So 4m ends up down here. And they're asking, will the they ask, how does the kinetic energy of this whole system compare to the value of 4 mgd? So what I'm thinking in my mind is that this 4 mgd value is connected to potential energy. This reminds me of this general mgh kind of a situation. And so there's a loss of gravitational potential energy here. And by conservation of mechanical energy, when I'm losing potential energy, I have to gain kinetic energy. So I think there's an equivalency here. If this is all part B, then in part C, I'm going to say same. That the change in the potential energy is proportional to the change in the kinetic energy. It's that the loss of potential energy goes into the kinetic energy. That's the kinetic energy of this rotating structure up here, as well as the translating structure down here. So the sum of all the kinetic energies is equivalent to the 4 mgd potential energy issue. And then they switch it around on us. Then they do this. So they ask us to consider what happens if they allow the system to be reset and the masses start from a hanging position like this. And then from that hanging position, they let the 4m mass fall down a distance d, and then they want us to compare the value of 4 mgd to the kinetic energy of the system, afterward. And so what I'm noticing here is that the change in potential energy that happens here is connected to both the kinetic energy of this system, but these masses, they swing up to a little bit of a higher position. So this little extra height that they each achieve as they swing up with their motion is an increase in potential energy. So the work done by the falling mass here both gives kinetic energy to this system and a little extra potential energy to the system as well. So afterward, the kinetic energy is going to be less than 4 mgd.